Okay, couple things. First of all, should have gotten exam 3 back here today. If you are at a point in this course where you feel like you need to discuss your status with me, please do so. But I will say, as a class, we did very well on this exam. I know some of us maybe aren't happy with their scores and didn't do so well, but collectively as a class, we did very well on here. I don't remember what the average or median was, but it was quite high compared to many previous classes I've had. So great job on that. If you are still struggling, however, with the course material, I just have the same suggestions as always: reading the book, doing your suggested problems, etc., visiting during office hours, forming a study group, and so forth in here. And just like before, if you do have any questions on your exams, I did place the answer key up there on Thursday, but you're always welcome to stop by my office and go through your exam with me if you do have questions. You were to have built a model of C6H14. I'd like for you to take that model right now and just set it aside. We're going to look at that in about half an hour. And then let's quickly go to those Socrative app questions. And I have those Socrative app questions right here. Do you have any questions on any of the Socrative app questions themselves? This is a review from last Tuesday. Yes, sir.
Can
Thursday.
Like, kind of go over them like real quick there?
Sure.
I missed a couple and I'm not sure which ones.
All right. Okay, first one. Help me out here. How many valence electrons are in one atom of carbon? 4. So it will form how many bonds? 4. Good. Next question was, the number of valence electrons in one atom of hydrogen is how many? 1. How many bonds will hydrogen form? 1. Good. Number 3 was, the number of valence electrons in an atom of oxygen was how many? 6. And it will form how many bonds? 2. Good. And then if we jump on to the fourth question, substances that have the same chemical formula but a different molecular structure are called? Isomers. I don't remember if we did that one, but this should have come from your lab. Okay. Number 5. Which types of carbon-to-carbon bonds are only present in saturated hydrocarbons? Single bonds. That's right. And question number 6 is, what is it they are saturated with? Hydrogen. That's right. They're saturated with hydrogen. And then the last one, unsaturated hydrocarbons must contain at least one of these 2 types of carbon-to-carbon bonds. They are double and triple. Any questions? We good? No?
Yeah, no.
Good.
I just, sorry. I didn't know which ones I missed. It said I missed a couple, but I agreed with all the. Don't worry about it.
All right, that's okay. At the end, you don't get graded on it. I just check to see if you're here. I already know you're here anyhow. So, anybody else with questions? All right. So today then, we're going to move on in organic chemistry, and I'm going to get my models out here because we're going to go through some of this stuff rather quickly. We'll start by just reminding you that we are looking at hydrocarbons. And when we look at hydrocarbons, there's 2 main classifications of hydrocarbons. And as the name suggests, hydrocarbons are made out of which elements? Carbon and hydrogen, right. So hydrocarbons are made simply out of carbon and hydrogen. And we have 2 broad categories of these. They are saturated hydrocarbons and they are unsaturated hydrocarbons. And as we talked about last Tuesday, if they're saturated, again, they're saturated with hydrogen, and all of the bonds again are single bonds. All the carbon-to-carbon bonds are single bonds. These here may contain more hydrogen, and that's because some of the carbon-to-carbon bonds are either what types? Double or triple bonds, right. So we're going to start with saturated hydrocarbons and look at those in more detail. As far as saturated hydrocarbons go, there's two main classes of saturated hydrocarbons. There are a class that we call alkanes and another class that we call cycloalkanes. However, your text only talks about this first type. So the only type that you're going to be responsible for in here is the alkanes. But when we talk about cycloalkanes, if you hear the term cyclo in there, that means that somewhere in the molecule there is a cyclic structure like a ring. Simply because we're spending only like about 2.5 class periods on this, there's no way we can go through all of the organic chemistry, so you're getting a very, very, very brief overview of something that we have an entire year-long course in. So again, you're just getting the very briefest of backgrounds with them. So we're going to start by looking at some of these saturated hydrocarbons, and again, specifically the alkanes. And first one we're going to look at is one of them that contains only one carbon, and I'm going to build some of these here as we go. This here would be the simplest of the alkanes. If you look at its formula, how many carbons do we have? And how many hydrogens? How many hydrogens here? 4, right? That's because, of course, carbon makes a total of 4 bonds, and each hydrogen makes 1 bond. So then if you were to draw out the structure for this molecule, it would look like this. And the name of this substance is called methane. This is what methane looks like. Then if we went ahead and picked up a second molecule, the next one we can look at then would have 2 carbon atoms present in it. So we'd write its formula as C2H. Now how many hydrogens on here? 6. So it'd be C2H6. Notice we had put the 2 carbon atoms together. Each carbon atom forms how many bonds? 4. So then if we put these all around here, we show those 6 hydrogen atoms. And the name of this one here is ethane. If we go on to the next possible structure, and again I'm just trying to build these very quickly from the little pieces that I have sitting out here. I build the next one that has 3 carbon atoms in it. It's going to look something like this here. And so 3 carbons in there. How many hydrogens will there be? It's going to be 8. Now if you're unsure, you can always build the what's called the backbone. And remember that each carbon is going to form 4 bonds. And as we put them in here, we put in 1, 2, 3, 4, 5, 6, 7, 8. So we put in 8 hydrogens. The name of this one here is propane. Now perhaps we're beginning to see some sort of pattern here. Let's say that we went on to 4 carbons. So we have C4. Following the pattern now, without even counting and looking at a model, how many hydrogens should there be? 10. Notice now, each time we add on 1 carbon, we add on how many hydrogens? 2. So then if you build that backbone, looks something like this. And then we can go ahead and add in the hydrogens, making it look like this here. Now, as far as the name goes, what do you suppose the suffix of the name would be? Ane, exactly. And this one happens to be called butane. Now, you've probably heard of at least 3 of these in here so far. My guess is you've heard of methane before. And where do we find methane? other than farts, which, by the way, not everybody makes. Only about 2/3 of us are methane producers, so the rest of us don't. Methane's colorless and odorless, so don't let anybody ever accuse you of producing methane. Methane is right here. Natural gas is primarily methane. Probably about 75% of natural gas is methane. Which other one have we seen up here before? Propane. Where do we find propane?
Gas grills.
Gas grills, exactly. That tank, there's a propane tank. You might label it as LP. LP stands for liquid propane. Butane, you've probably heard of, but probably only if you smoke. Right, lighters. Okay, so those are butane lighters. And so again, these are things that if we think of what they're associated with, we have methane in here, we have propane, we have butane. Those things are essentially associated with burning things, with fire. We typically burn hydrocarbons. Okay, so again, all of these have a suffix of A and E. Now the other thing we noticed as we went along, remember that each time we added in a carbon atom, we added in how many hydrogens? 2. Of course, now we started the first one. The first one actually started with 4 hydrogens. So it turns out that we can look at the alkenes with a general formula, and we say that the general formula is CnH2n plus 2. Have a general formula of CnH2n plus 2. That means if we know the number of carbon atoms, the number of hydrogens is 2 times the number of carbons plus 2 more. So you see how that pattern fits. If we have 2 carbon atoms, 2 times 2 is 4, plus 2 more gives us 6. So if we wanted to go on to the, we don't need to go on to the next one, but let's say we go up to one that has 7 carbons in it. How many hydrogens would that make? Again, 16. And that's because 2 times 7 gives us 14, plus 2 more gives us 16. So its formula is C7H16. If we drew in the backbone, we'd have 1, 2, 3, 4, 5, 6, 7 carbon atoms. We can then go ahead and place all around here hydrogens. And there we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, just like we predicted. Again, the name of the alkanes will always end with ane. And once we get beyond 4 carbons, then we start using the Greek prefixes we already learned before. So you might remember that pent means 5, hex means 6, and the prefix that stands for 7 is hept. And so we call this one here heptane. Heptane. Now, on page 654 of your text, it will give a table for you, and I don't think you really need to pull this out right now because we're just going to duplicate this. But your success in organic chemistry is going to depend upon your ability to count carbon atoms. If you can't count carbon atoms, then you will not have success with organic chemistry. So we're going to look at the number of carbon atoms and what their associated prefix would be. So we'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And starting with number 5, they go by their Greek prefixes. Now, the Greek prefixes aren't going to include the letter A, because remember when we went through inorganic nomenclature, we said it was penta, hexa, and so forth. So we'd write pent. 6 again was hex. 7 was hept. What is 8? Oct. 9, non or non. And 10 is dec, like decade. Okay, so these are ones that we've already gone through. Here are the new ones for dealing with carbon atoms. And they are the prefixes meth, eth, prop, and bute. And of course, we already looked at those 4 alkanes already. We had methane, ethane, propane, butane. So now, let's say we want to go to something that has 10 carbons in it. If we want to have something that has 10 carbons, it's going to have how many hydrogens? 22. And it has 22 because our general formula says we take the number of carbons, multiply it by 2, and then we add 2 more. So it's going to be C10H22. The name of this one here is going to be? Decane. That's right, decane. Now, we probably are getting tired of writing all those carbons and hydrogens down, so let's try to avoid writing out all those bonds because that takes a long time. What we're going to do instead is we are going to use something called condensed structural formulas. Condensed structural formulas. And a condensed structural formula is one which we know in advance, without me telling you or anybody telling you again, that carbon is always going to form how many bonds? 4. Hydrogen is always going to form 1 bond. Okay, we don't need to be told that again. Carbon always forms 4, hydrogen always forms 1. Since we know that, we could then go back to something like the heptane. If you look at heptane, you'll see that this carbon here is attached to how many hydrogens? 3. This one here is attached to how many? 2. This is to how many? 2, 2, 2, 2, and on the end there would be 3. So then what we do for heptane is we'd write out the structure for heptane like this. We'd write it as CH3, CH2, 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 CH2. That's 5 of them. This makes 6. And on the end here now, this makes 7. So this would be what we call a condensed structural formula for heptane. Now we could condense this even more. Any ideas how we might condense this even more?
Can't you do CH2 and put that in parentheses?
Yes, exactly. So again, we take the CH2, put it in parentheses, and then outside the parentheses we put a 5 to indicate that that unit has been repeated 5 times. So we'd write it as CH3, CH2, parentheses 5, CH3. And each one of these here are different examples of condensed structural formulas for heptane. So now let's go back to your decane that you had back here. Let's write out a condensed structural formula for decane. Write a condensed structural formula for decane. Now remember, carbon is always going to form 4 bonds. Hydrogen is always going to form 1 bond. So if you think about what has to happen, the carbon atom on each end is going to have how many hydrogens? 3. And all the carbons in the middle are going to have how many hydrogens? How many in the middle? 2 on each one. So again, write out the condensed structural formula for decane. And you can write it either way, like we did for heptane. Each of these are correct condensed structural formulas. So now when we write it in for decane, on the left-hand side we'd write CH3, and then what could we do next? CH2, and if we want it the shortest way possible, what could we do with the CH2? parentheses and 8, and then on the right side, CH3. And if you wanted, you could write the CH2 8 different times in a row. And that's fine, and that's a condensed structural formula. And that way, when you see that, what you know is that CH2 unit has been repeated a total of 8 times in the center. And you see a total of 10 carbons that's contained in here. Then as far as the number of hydrogens, the hydrogens should be 22. So if we count these here, we have 3 and 3, which is 6. 8 times 2 gives us 16. 16 plus 6 gives us a total of 22, which matches this number out here. And so it's always good to check your math as long as you know your general formula for the alkanes being CnH2n plus 2. Any questions that you have on that one there? Okay, now, sometimes even writing it like this is a pain in the butt. It takes too much time. So what we do then is we use something called a line structure or line formula. These here are the same thing. And what we do is we wind up writing out, basically it's going to look like a bunch of zigzags. And we count 1, 2, 3, 4, 5, 6, 7. And I didn't mean to put that little wing on the end. So 1, 2, 3, 4, 5, 6, 7. Right there. And if you were to look at this now, what we'd see is a total of 7 points on here. We count 1, 2, 3, 4, 5, 6, 7. This tells us that we have a total of 7 points, and each of those points represents an atom of, what do you think? Carbon, exactly. It represents an atom of carbon. Now, we're all smart enough to know that carbon is always going to form how many bonds? 4. Hydrogen is always going to form 1 bond. So if you were to look at this then, you know that a carbon sitting here is going to form bonds to how many hydrogen atoms?
2.
2. Because 1 goes to this carbon, 1 goes to this carbon, and then there'd be 1 hydrogen here on each side. So this would be an example of a line structure for heptane. So again, these are all heptane. This is heptane, this is heptane, this is heptane as well. And if you go in to use a program called Marvin Sketch, how many of you have done any of the problems in Mastering Chemistry for Chapter 18 thus far? Okay. Marvin Sketch is the program that, there's lots of chemical structure drawing programs out there. Marvin Sketch is one of them. We use another one called Chem Draw in our labs and Chem Sketch. So we have like 3 different ones here at Anoka Ramsey. But the one that Mastering Chemistry uses is called Marvin Sketch. So this is just the name of a program. It's not the type of structure, but it's a program that's used. When Marvin Sketch draws it, it draws it like this. It writes it basically what we just saw. So there's 3 points, 4, 5, 6, 7. But on the end, it shows what we call the terminal carbons. It calls the terminal carbons. And terminal, this is not just chemistry now, but if something is a terminal something, what does a terminal something refer to? What does terminal refer to?
End.
Something that's on the end. So in Marvin Sketch, it shows the terminal carbons. So something like this, we would still say has 1 carbon here, 2, 3, 4, 5, 6, 7 carbons. And so again, it shows the terminal carbons when you put this into Mastering Chemistry. So again, I'll put as Marvin Sketch or MC for Mastering Chemistry. And again, these all represent the same thing. Now, your author, turns out, likes to also write his left-hand carbons in reverse. And the same thing. So if in case you would quickly turn away and say, oh, something changed, here's what changed. Notice now I'm writing as H3C. That's the same thing. And what it actually reflects is that on this end, which is your left end, it's actually showing the hydrogens out here on the left-hand side to you with its carbon. But either convention is correct. You can either write it here with these carbons, with the hydrogens shown on the left-hand side, or you can write it with the carbon shown on the outside. This is how I learned it when I was a student. However, it's turning out just like Marvin's sketch is using it here today. This is actually probably more of a British convention, actually, and a lot of these programs were designed in Europe. But writing it either of these two ways then is a equivalent way of writing them. So again, they all represent the same thing. And you should know all of those different possible representations of the structures when you go through your homework. Okay, so it's important. Yes, Brianna?
So then you don't have to label the line with anything, you just draw the line and that's it?
You just draw the line and that's it. So if you're, and that's why if you look at a structure, let's say that you went and looked further, maybe not so much in this chemistry textbook, but perhaps in our more advanced text, and I won't pull out an exact example there, but if you were to look at something out of there and you saw a structure that looked like this, what this will tell you now, if you look at it, and this should be all joined together, you can tell exactly how many carbon atoms are in here. How many would there be?
6.
There'd be 6 carbons in here. All those carbon atoms would be joined in a ring, and each carbon that's shown here is attached to how many hydrogens? 2. Okay, because remember, you're showing one bond to this carbon, one bond to this carbon, so if this carbon's already making 2 bonds to other carbons, then it can only have 2 more hydrogens in there. So and then those hydrogens would come off like this out around that structure. So yes, and if you go on into organic chemistry, you'll see that in our organic chemistry textbook, we even rarely write condensed structure formulas. Pretty much everything is written as line structures in there. Okay? And part of the reason for that is because when we deal with bonding, remember that all of our bonds and all the electrons in molecules, either as lone pairs or bonding pairs, are always paired up. They don't show up as individual electrons. So one of these lines here is already representing 2 electrons in a bond. Okay? Anybody else? Did that answer your question? Okay. Anybody else? All right, so now you can go through and you see these websites with these beautiful structures in chemistry. You should be able to understand all of them. Okay, next up, what we're going to look at is something called an alkyl group. An alkyl group. Now, we notice that we're going to have to pay attention to prefixes and suffixes and such in here. So, when I talk about prefixes and suffixes, for example, I'm talking about the alkanes. Again, notice all of the alkanes end with A-N-E. All the alkanes end with A-N-E. So now we're going to look at an alkyl group. And what an alkyl group is this. We say that an alkyl group is an alkane that has had one hydrogen atom removed. An alkyl group is an alkane that has had one hydrogen atom removed. And now I'm underlining portions of the name. Notice we changed the A-N-E suffix to YL. And when we do that, we form this alkyl group. To name the alkyl group, we are going to drop A-N-E from the alkane name and we are going to replace with a suffix of YL. So again, we take off A-N-E from the alkane name, we replace with a suffix of YL. So if we come to this alkane right here, if I take one hydrogen off of here, so now you see there's how many hydrogens? There's 3. We would then write that structure like this. in terms of a condensed structural formula, we'd say CH3 dash, and that dash isn't representing, what this dash is representing now is a bond. So that means that this now can bond to something else because it has a space available to do that. Now if we follow this convention, what name would we assign to this alkyl group? So again, we're going to follow this convention. It's going to be a methyl group, exactly. And it's going to be a methyl group because the way we'd name it is, if it had all 4 hydrogens in there, we would call it methane. But now we take the 1 hydrogen off of there, and it now can bond to something else. We replace the A-N-E suffix with the suffix of Y-L, and we call this here a methyl group. Now it turns out that methyl groups can attach themselves to all sorts of things. This here happens to be something called benzene. And if we take a hydrogen here off of this benzene, we can now stick this methyl group onto here, and this becomes called methylbenzene. So we name it then based on the group here that is attached to this structure. And so again, this here is a methyl group. Next up, we have something like this. We take a hydrogen off of here. This now is the one that had 2 carbons. If we wanted to name this one, we have CH3, CH2, and this then can form some bond to it, a bond to something else. The name of this group is going to be called a ethyl group. This here is an ethyl group. And it's an ethyl group because if we went back to the alkane, which would be CH3, CH3, with 2 carbons, the name of that alkane would have been ethane. We then drop the A-N-E suffix off of there, replace with Y-L, and we call it an ethyl group. Let's look at this one here. CH3, CH2, CH2. The name of this one here is going to be called propyl group. It's going to be called a propyl group. And that is because if you go back to the structures we were looking at back here, if it had 3 carbons in there, we call it propane. We take 1 hydrogen off of there. We take the hydrogen off, that makes it a propyl group. And if we then attach this propyl group to something like this, which is benzene, the name of this then becomes propylbenzene. So again, if you can't count carbon atoms when it comes to organic chemistry, then you're going to find yourself in trouble. So you do need to know these prefixes because those prefixes again are an indication of the number of carbon atoms in the molecule. Now when it comes to this propane, one of the things we need to remember about single bonds is that single bonds always allow for rotation along the axis. And all of these single bonds are always moving around. So if I take one up here off of the top, taking one off the top is the same as moving one off of the bottom. So all of those positions are equivalent. It doesn't matter whether I take it off the top, bottom, side, or whatever, because single bonds are always spinning around. Likewise, how does this compare if I were to take one here off of the right-hand side? It's the same thing. Why? All you got to do is flip the molecule around and it's the same thing. So it's just kind of like me. If I took my arm off of here like that, if I spun around, it doesn't matter here. I still got an arm missing. Okay? And so if I take one here off of this side, or I take it off of this side here, as long as we can spin it around, it doesn't matter. All of those hydrogens here are equivalent to each other. However, where could I take that hydrogen off to make it different? Off the middle, exactly. So I take it off the middle now, that's not the same as taking it off the end. And so this one here has a different structure than the one that we just looked at. And because it has a different structure, it also has a different name. And so the way that we would write that is like this. We'd show it as CH3. Notice now how many hydrogens are attached to that middle carbon atom. Just one, because there were two. I took one of them off. And so I'd write it then as simply CH, and then I'd put CH3. And then we could show that it forms a bond. Now whether I show it coming off of the top or showing it coming off the bottom, it doesn't matter. Because one is simply like this, upside down. You see the free bond here. I could turn it like this. They all represent the same thing. So top or bottom, they all represent the same thing. Now because it is different than the previous one, it is an isomer of the previous group, we call this an isopropyl group. And the prefix iso comes from the fact that it is an isomer of the propyl group. And again, we refer to it as an isopropyl group. And you've probably heard of isopropyl before. Where? Rubbing alcohol, exactly. Turns out that rubbing alcohol is made like this. You basically take this isopropyl group and you add on an OH. And as we're going to learn on Tuesday, or possibly next Thursday, what makes an alcohol is going to be the presence of an OH. So it's called isopropyl alcohol. And this is the structure of isopropyl alcohol. So if you hear that name, isopropyl alcohol, you hear the prop, right away that's going to tell you that there are 3 carbons in there. If you go to the gas pump and you fill up with gasoline, it's going to talk about blank ratings. What type of ratings does gasoline have?
Octane.
Octane ratings, exactly. That's because they contain octane. So in that gasoline there's going to be something that contains how many carbons? 8 carbons, exactly. It's an alkane with 8 carbons. If you look at something like methamphetamine, well, methamphetamine, of course, is a drug, but you hear the prefix meth in there, and that's going to tell you there's something in there that has 1 carbon contained in there. So you'll start listening to these names now. Look at a bottle of shampoo in session. You're going to start seeing all sorts of these names that are very common based on the number of carbon atoms that are contained in these molecules. And then the last one we'll look at here today would be like this: CH3, CH2, CH2, CH2. The name of this one here, go back to what the alkane is. Remember now we've taken a hydrogen off at the end. We're showing a bond. Pronunciation is going to be important. It's not butyl. It's the butyl group. Now in your text you're going to see a bunch of these structures, and I don't have a page reference here, but this is in chapter 18, and I am going to find a page reference here for you right now. This is probably I'm looking around page 651, 652. Here we go, page 654. Because it's on the one that I already listed, page 654. And it's going to show some more of these common alkyl groups. So here are the number of carbon atoms and the associated prefixes. Here then are also some of the different alkyl groups. Notice now the way that your author is showing them is showing these bonds. This one's not working. What about this one here? Showing these bonds coming out the left-hand side, and that's okay. So we just removed the hydrogen from them, and this is a methyl group. Now it's showing a few more in here. How many of these do you need to know? The ones you need to know are the ones that we just wrote down here. You need to know methyl, ethyl, propyl, butyl, isopropyl. So you need to know these first 5 that are on page 654. And part of the reason why we only need to know these first 5 is because once we get up to this many, the names and structures get to be a lot more complex. You'll see that once we get up to 4 carbons, we have butyl, isobutyl, secondary butyl, tertiary butyl, and that's simply because of carbon making 4 bonds. There's several different ways to make those 4 bonds and have something come out of there. Beyond that, you should also then be able to name anything that is straight chained. And by straight chain, this is something that is straight chained. This is something that is branched. So anything beyond 4 carbons, you should know the straight chain name of an alkyl group. So even if we had something like, I think this one here has 6 carbons in it, and by straight chain, this is what we refer to as straight chain. There's 6 in a row. If I take a hydrogen off at the end, the name of this one here is going to be called a hexyl group. The name of the alkane itself, with all the hydrogens in there, this is going to be called hexane. And we take the 1 hydrogen off of there, this here is going to be called a hexyl group. So anything that is straight chain, you should know beyond 4 carbons. Going up to 4 carbons, you need to know these first 5 that are on here. Don't worry about these here that have branching off them down below here. Okay, so any questions on those expectations? All right, what I'm now realizing is I forgot to print something out here for you this morning. So I'd like for you, if you did not finish your C6H14, I'd like for you to finish your C6H14 right now. Go back and compare your models to each other. And while you're doing that, I'm going to make a printout that I'm going to grab from the computer. I forgot to record the last half hour. I'm sorry if you're listening at home.